Okay, so now we are going to look at how to test whether a particular schedule is serializable or not. So that is given a schedule of execution of transactions. We are going to check whether it is a serializable schedule or not. So in order to do that, what is done is first we have to build what is known as a precedence graph or a serialization graph. So it's a graph. So graph is represented always like this, right? G is equal to NE, where N is the number of nodes and E is the number of edges. Okay. The number of nodes, the nodes in this particular precedence graph or serialization graph will be the transactions. Say if there are n transactions, T1, T2, etc., Tn, then those are the nodes of this precedence graph. And there will be edges between these nodes also. And so each edge EI is of the form Tj to Tk, where Tj is the starting node and Tk is the ending node. Now, such an edge from node Tj to Tk is created by the algorithm. There is a pair of conflicting operations which exist in Tj and Tk. So an edge is defined between two nodes Tg and Tk if there is a conflicting operation between these two transactions, and the conflicting operation in Tj appears in the schedule before the conflicting operation in Tk. Okay, so that is how we draw the edge between two nodes. It is there should be conflicting operations between um, uh, conflicting operations in the transactions Tj and Tk, and at the same time the conflicting operation in Tj appears before Tk. That is why we draw a node edge from Tj to Tk. Okay, so so how do we draw this? So the algorithm for each transaction Ti participating in the schedule, first of all we have to create a node which is labeled Ti in the precedence graph. So we have to create the nodes, and then creating edges means the edges from some transaction Tj to Tk, and Tj and Tk will have conflicting operations. Conflicting operations means uh, operations which belong to two different transactions which involve the same data item, and one of them is a write operation. That is what conflicting operations we had defined earlier. So for each case in the schedule where Tj executes a read item after Ti executes a write item, then you have to create a node from Ti to Tj. Okay. So Ti executes a write X first, and after that Tj executes a read. So read and write are conflicting operations, since here they are actually belonging to two different transactions Ti and Tj, and one of them is a write. So similarly the other cases are one write and the other read. Okay, here for this case, Tj executes a write item after Ti executes a read item. So Ti is the one which executes the first conflicting operation. So the edge is from Ti to Tj. And similarly, the other conflicts are between two write. So that is what we said. Conflicting operation means you have a read item in Tj and write item in Ti, or a write item in Tj and read item in Ti, or both are writes in the case of Tj and Tj. Either way they're conflicting, and the edges from Ti to Tj when Ti, the conflicting operation Ti executes first. So this is how we build the precedence graph. So first of all create the nodes, then create the edges. And the schedule is serializable if and only if the precedence graph has no cycles. Okay, there should not be any cycles. If there are cycles, means it is not serializable. Okay. Okay, now we will look at an example. So these are schedule A, B, C, D, which we had earlier seen also. In earlier discussion also, we had seen the schedules, these four schedules. Okay. And in schedule A, we look at it, we know transaction T1 is completely executed before transaction T2. So this is a serial schedule. T1 is executed first, followed by T2. And in the case of schedule B, it is a reverse. T2 is executed first and then T1 is executed. And in the case of C and D, we have a interleaving of executions. So what we have to do is for each of these schedules, we want to draw the precedence graph and find out whether each of these is serializable or not. Okay, so first of all, we have to draw the nodes. Okay, so T1 is the first node. There are two transactions in the schedule. So we will draw two nodes, T1 and T2, and then we have to draw the edges. So are there any conflicting operations? If you look at this, we have got a read item X. So is there a conflicting operation here? This read is not conflicting, but this write is conflicting. So the first conflicting operation is in T1. So we have an edge from T1 to T2. That is how we draw. Okay. So next is we have a write item X here and a read item. These two are conflicting. So T1 to T2 again. So we have already drawn the edge, right? So we may also label what particular data item is the conflicting item. That also can be represented in a precedence graph. Now we have got a read item Y, but there is no conflicting operation here. Write item also there is no conflict. So this is our precedence graph. So here we see there is no cycle, and so it is actually a serializable schedule. Basically, it is a serial schedule. So it is okay, right? It is serializable as well. And similarly, again, this schedule B also, it is a serial schedule. Again, we will draw T1 is the first node and T2 is the second node. Here we will look at read item X is the first one which is read. This read item is not conflicting, but write item X is conflicting. But here T2, in T2 the first conflicting operation is executed. So we have an edge from T2 to T1, the reverse. Okay, next we have got a write item here and we have got a read item. These two are conflicting. Again, it is T2 to T1. That is how the edge is there. So again, if you look at this, for read item Y and write item Y, there is no conflicting operation here. So this is our precedence graph. And since there is no um, cycle, so this is a serializable schedule. Now we look at schedule C. Again, we have to start with the nodes T1 and T2. Okay, T1 and T2. So here in T1 we have got a read item and there is a write item here, right? So T1 to T2 we have to draw because read actually is executed first. Now we will come to this write item. So we know here a read item is there here and a write item is there here. So we have to draw in the reverse direction, right? And corresponding to Y, there are no conflicting operations in T2, so that is okay. But if you look at this, there is a cycle, right? This is a cycle. So which means this is not serializable. Okay. Similarly, we can look for schedule D also. Schedule D, it is not, look, this only this has a cycle, others there are no cycles, so they are serializable. So this is serializable and is equivalent to the serial schedules A and B. Okay, now we look at another example which involves transactions T1, T2 and T3. So there are three transactions involved in the schedule. So this is schedule E. So we can draw T1 is the first node and we have got T2, T3. Okay. Okay, now what do we do? So here we have got a read item X here There are no read items here. Okay, we have got a read item X here, but there is a write item X here. So which means you there an edge from T1 to T2 has to be there, right? There has to be an edge from T1 to T2, and we have got a write item X and a read item X. So again, T1 to T2 is there. But here, if you look at this, this is read item Y. Okay, there is a read item Y and the write item here. So since this is executed first, we have to draw from T2 to T1. Oh, okay, T2 to T1. We have to draw like that. Similarly, we can look at T1 and T3. T1 and T3, there are no X items being read here, but Y is being read. So you have read item Y and write item Y is here. So which means from T3 to T1, there is an edge, right? T3 to T1. Similarly, we can look at T2 and T3. Z, there is a read item Z here. There is a write item Z also. So we have to have T2 to, okay, and so on. So if you look at this, there is actually, if you look at this, okay, maybe we can label it also. Like we said earlier, actually a cycle is there. Even without the labels, we will be able to understand from T1 you go to T2 to T3 to T1, right? So this is a cycle. So when there is a cycle, we know that it is not serializable. Okay. So this is the uh, what precedence graph corresponding to schedule E. Here the labels are also seen based on which particular what data item conflict happens, that is also mentioned. Okay, now we will look at schedule F. Okay, in the case of schedule F also we have got T1, T2, T3. Those are the transactions involved. Again, we look at here, we have got a read item X, and here we have got a write item X also, which means T1 to T2, and edge is there. There is a write item X, and we'll also label it. Okay. Right item X here and the right item X, they're conflicting. Okay, that is fine. Now read item Y, here is also here also right item Y is there again, T1 to T2, so which means based on Y also there is conflict. Okay, now let us look at T1 and T3. So we have got okay, we have got read item X is not there in this transaction T3, so there is no conflict with respect to X. But read item Y is shown here. Write item Y is shown here, which means T3 to T1 we have to have an edge. Okay, and it is a label based on Y, and Z is not there. So T2 and T3, let us see. We've got a read item Y here. We have got a write item Y also, which means T3 to T2 is there. So we need an edge from T3 to T2. Okay, which is based on Y. Okay. Uh, and Z is, there is no right for Z here. No conflict will be there, right? But here we okay, we've got a write item Z here and a read item Z here, which means T3 to T2 again based on Z there is a conflict. But if you look at this, there is no cycle, right? T3 to T1 to T2, but not again to T3. So there is no cycle. So this is actually serializable. I think Actually, this is the equivalent one. There is an edge from T1 to T2 based on X and Y, T3 to T1, Y alone, T3 to T2, Y Z. Okay, the same graph, what we have drawn here. Okay, the same graph is actually drawn here also. Okay, so this is how we draw the precedence graph, and we said that when there are cycles, there are no equivalent serial schedules are not there, since there are cycles in this graph. But in the case of those without cycles, equivalent serial schedules can be actually written down. So basically what this means is, the edge actually means T1 to T2 there is an edge, means whenever we are executing transaction, or in transactions, these transactions T1, T2 and T3, T1 has to come before T2. Okay, that has to be ensured. Similarly, T3 has to come before T1. Okay, and T3 has to come before T2 also. So which means T3 has to come before T1 and T2. So here we are saying T3 is executed first, and we know T1 has to come before T2 according to this edge. So then comes T1 and T2. So this is how equivalent serial schedules are drawn. Okay, so this is another example. So here it says T3 has to come before T1. So it is there, and T3 has to come before um, T2 also, both T2 and T1. So it is mentioned first, but there is no precedence mentioned between T1 and T2. So we can have two schedules. First T1 can come or T2 can come here, either way. Okay. So this is how, given a schedule, we are trying to find out whether it is serializable or not. So basically what we do is we draw what is known as a precedence graph. So in order to draw that, first we have to convert every transaction into a node, and the edges have to be drawn if there are conflicting operations between the this, and you check whether there are any cycles involved. If there are cycles, it is the schedule is not serialized. Okay. Now, in practice, actually, it is difficult to test for serializability of a schedule, because we have interleaving of operations from concurrent transactions, and what operations are executed at any point in time is actually decided by the operating system scheduler, right? You have already come across operating system and how the different processes are executed, and which processes executed at a time is decided by the OS scheduler. Similarly, here also which transaction is executed is decided by the operating system scheduler. So there is no way we can decide which one is going to be which of these operations, read item X or write item X, is going to be executed. Okay. So it is difficult to determine how the operations of a schedule be interleaved beforehand. Beforehand, only if we get the operations beforehand, we will be able to draw a graph and decide whether a particular schedule is serializable or not. And another problem is transactions are submitted continuously to the system. So it is difficult to determine where a schedule begins and where it ends, and so on. So there are so many practical difficulties about using a precedence graph in order to decide whether a particular schedule is serializable or not. So the approach taken by most commercial database management systems is to design protocols, and which are followed by every individual transaction, that will ensure serializability of all schedules in which the transaction participates. Okay, some sort of rules have to be framed, and which has to be followed by all the transactions in order to ensure serializability of all schedules. And commonly used protocol is two-phase locking protocol, which we will look at next.